Hi everyone, my name is Kendall Nelson. I'm 26 years old and I'm a student at UWSP, currently in the Mathematics Application Course 105. Today for my project I will be doing a presentation on how mathematics is involved in the fire service. I've been a firefighter now for about 5 years and I'm actually going back to school for my bachelor's degree. Today I'm going to talk about the math that's involved in the fire service. After putting this all together, I didn't truly realize how much math was involved in the fire service. So I'm going to start talking with my firefighting gear. Then I'm going to talk about one of the trucks that we have that flows water through a hose and that goes out onto a fire. And then I'll talk about some other equations that we have to use in the fire field in order to successfully do our job. So first we're going to start off with my firefighting gear. So I know in class this year we spoke of algorithms. I know the professor spoke of algorithms, some simple things like tying your shoes, making a bowl of cereal, whatever. Well, this algorithm that I have is involving putting on my firefighting gear. As you know, firefighters need to put on their gear as efficient and as fast as possible. So this may look kind of silly, but I already have my pants in my boots so that when I get here, all I have to do is take my shoes off and slip right into my boots. So now, as you can see here, that's a different color, and then they have the reflective on the bottom for us to be seen better in smoky environments where it's really thick. The other layer keeps the heat out, but it keeps the heat in as well. So suspenders to help keep everything in. The next piece that I'm going to talk about, which is not in order, is the air pack. So this is like an backpack. These are shoulder straps. Here's a back support. This is the mechanism that holds our air bottle. So when we're talking about math, we have an air bottle here. That is what we call a 4,500 PSI bottle. That's how many pounds per square inch is in here of compressed air. This is what firefighters breathe. If you look at this dial down here, it's a gauge. You see it says PSI times 100. So that means on the dial where it says 45 in the green, that means the bottle is completely full. So 45 times 100 is 4,500. That's the max amount of compressed air that can be in this bottle for us to breathe. So one thing with these bottles that's really important is that we have them full, and we also make sure that the bottles are connected properly, because just like anything in math, if something isn't connected properly, it's not going to work out. The next portion that I'm going to talk about is my helmet. These helmets kind of look funny, and no, they don't go on like this, like a ball cap. They go on with the brim in the back. So one thing that somebody noticed, along with the historical piece of the helmet, is that the helmet itself is roughly 7 to 8 pounds. This brim on the back is meant for if falling debris, water, and things like that in a fire hit this, it allows it to deflect easily and counterweight the balance of the helmet. So if I put this on, it helps counteract the weight of the helmet. It's really important for a firefighter to be completely covered 100%, because when we go into a fire, we do not want to have any skin, hair, clothing, anything like that showing. Next, I'm going to talk about my jacket. You can see there's 2 layers. I'll unbutton this for you. This is the layer that's protective and thermal. This is also a thermal layer that helps keep the heat out. This turnout gear can be in an environment up to 500 degrees for a consistent 5 minutes before any type of damage starts happening to this material. It's called fire resistant, fire retardant. Although people think it's called fire resistant, it's resistant for a certain period of time. So this is a part of the algorithm. Like I said before, us firefighters need to be fast and efficient in getting this gear on. Next, this is my face piece that I'm going to place on. Now I'm gonna wait to put this on because it's kind of hard to hear me talk. But once I connect into air, you'll be able to hear me. I have like a little microphone. In here, it allows me to breathe in air and exhale without breathing any smoke or any chemicals or anything that might harm me. It's a part of that algorithm. So I put it up to my face. And I pull. And then I tighten the head straps. We don't want any leaking air. This is a strap to come right around my head. So I'm going to put my backpack on. Put it on like a backpack. Got a buckle in the front. Big buckles here. Tighten it up. Cinch these parts down. Now it fits on me nice and snug. Now one thing where that hood is, where I put it, so I'm going to come up and around this strap to get my hair out of the way, and this cups right around my face. I want to be completely covered. I don't want anything showing. Take this strap, helps cover my neck. You're going to hear a bell. This is me turning my air pack on. It's going to make a lot of different beeps. So as a firefighter, when I have this air pack on, now you're going to hear me through my microphone. When I have this air pack on, I can't see that gauge in my air pack. So you can come on here and I have my own gauge. So if you remember, 100 times the PSI that's listed, so it's around 40, 41. So 41 times 100 is 4100. I can also do this and click on. It tells me 4165. So now one thing I can do is I can latch into my air. And now you can hear me talk. You can hear me talk through this little microphone. Last two things are my helmet and my gloves. Just going all the way around. Just it a little bit. Nice and tight. And I have my gloves. So as you can see, I am completely covered from head to toe. I'm ready to go into a burning building. Anything that's on fire, any hazardous area, I am covered completely. My head, my neck, my hair, and everything. So that was the algorithm. Now firefighters for a state exam are required to do all of this in 2 minutes. It's called the 2-minute drill. When I went through school roughly 5 years ago, I could get this done in roughly a minute. It's something we practice, something that's very important. One thing that I would like to discuss next before we actually go into a truck and flow water out of a hose is something called gallons per minute, GPM. That's something that us as firefighters find very, very important. That means that that is the number of gallons of water that can be pumped out of a certain truck, engine, certain type of fire vehicle. One thing that's really important for us to not only know that with the fire truck, but one thing when it comes to us calculating that and how much we'll need at a fire is a super easy algorithm. It's length times width divided by 3. If you have a room and say you enter, firefighters enter right here with a hose. If you have fire up over here, me as a firefighter, I'm gonna say, okay, this room is 10 feet in length 10 feet width. So if we take length, which is 10, width, which is 10, which equals 100, and you divide it by 3, we're roughly looking at 33 gallons per minute, which truly isn't a lot. This is a small room. So if the fire was this big, how does that change, right? Our length and our width are the same. That's how many gallons per minute of water you're gonna need. Another thing that I realized with math is something called the fire load or the fuel load. Now, if this room was completely empty, as if somebody just moved out of their apartment and there was nothing in there, it was a flooring and walls, what we would call is fire load. The fire load is small. That means that there's not a lot of items in there to burn. Now, if you have a room that is the same size, and say you have a couch, and maybe your TV is over here on a TV stand, and maybe you have a recliner over here, and maybe you have an end table, and maybe you have another big table in the center, and maybe a big area rug. All of those things accumulate and add up into the fire load. So that means now going from an empty room, you now have this TV in the stand on fire to catch fire. You have this couch that can catch fire, this big area rug, this big table, this end table, and this big recliner. So that means that those are all different things that can catch on fire. So that would mean that your fuel load would increase. So the more that's in a room, it increases your fuel load. The less that's in a room decreases your fuel load. This is important for us as firefighters to determine so that we get an idea of the amount of water that we will need to put out maybe a fire in this corner versus all of these different things that are caught on fire. One thing as firefighters that we worry about is something called friction loss. That's friction. So if you have a hose, and this is your nozzle. There's different types of hose. There's rubber, there's some other different materials. When the water flows through here, it's not just free flowing. It's not only pressurized by the amount of pressure in PSI that we engaged to increase the gallons per minute. It also has to worry about the sides of the hose. This is where we come in and talk about friction loss. So as that water runs past this, it slows down. It causes friction within the hose. It's very, very important for us as firefighters to notice that when we're pumping and flowing water. Because if we have, say this is a 50-foot length of hose, our friction loss could be very, very minimal. So if you had, say this was double that, your friction loss is going to increase. So the more amount of hose that you have out, so it could be 50, it could be 100, it could be 150, it could be 700. The more amount of hose that you have out in order to get to a fire increases the amount of friction. There's more areas for that water and that material to cause friction and reduce the flow and the pressure of water. So I don't have the time on a fire scene to calculate this formula. But one thing that's very, very important for us to pay attention to is your hose diameter. So different types of hose diameters can include 1.5 inches, 2.5 inches, or a 5-inch. These are lines that we use most of the time, 1.5 and 2.5 inch. Another concept is hose length, like we talked about before. The greater the hose length, more the friction. So this 500-foot amount of hose is going to have more friction and more of a friction loss than any of these other two. The third item is the water rate, or the flow rate at which your water is flowing. So this coefficient right here is something that's predetermined. The coefficient is a dimensionless number defined as a ratio between normal force and friction force. So there's always going to be some type of predetermined value here. And on our trucks, we have charts that we use to allow us to go, yep, this is the size hose, this is the amount of length, here's roughly the friction loss that we're going to have, so that we don't have to do this calculation on a seam. So Q is going to equal the gallons per minute, which is your flow rate. L is going to be the length of your hose. And the C coefficient is a predetermined friction loss coefficient. So if you put numbers into these, you can figure out what your friction loss is. Ultimately, as a firefighter, as long as you know that the more hose that you have out there and the bigger the hose, the more friction loss that's going to impede on your gallons per minute and the flow that you want your water to be flown at. So first I'm going to talk about some different things, obviously, that apply to math, and then we'll actually go through the algorithm of pumping. You have to know your pump capacity, meaning how many gallons of water per minute does this pump is its max. There's a label right here that says roughly 1,500 gallons of water per minute can be flown out of here, which is a lot of water. That's big water. Another thing is that we have to realize that the type of hose that we're using, the type of nozzle that we're using can all affect the water flow. We're also worried about the PSI. So the pump has the ability, as well as I do, to either pump in pounds per square inch mode or in RPM mode. I've been taught both. It doesn't matter. It's good to know both and have those in your toolbox. So as you can see, it's really important to have the labels and the gauges for each pump. This right here is your pump intake. That's the amount of water that somebody is putting in the pump to make sure that the tank stays full. This here is your pump discharge. This is important because this is telling you how much water is going out of the truck. It's really important to watch your gauges. Like I said, all the gauges on here are in PSI mode, but something down here that I can use is either PSI pressure mode or RPM mode. So this here is what we call an 1.5 inches, or some people say 1 3/4 inches, because sometimes there's a difference between the diameter, the inside diameter versus the outside diameter. So this is the type of material that hose that we use. It's flexible, you can move it. When it is charged, what we call, means full of water, it is very hard to bend, it's very hard to manipulate, and it's very heavy. One thing, if people don't realize, that roughly 1 gallon of any type of fluid, whether it's milk, water, juice, what have you, it roughly weighs about 8 pounds. So this hose roll here is strategically rolled in a circle so that when we get on the scene, I can take this and roll it out to be as effective and efficient as possible to get the hose straight so that we don't have any kinks. Again, like I talked about before, this is the nozzle. This has a lot of effects of how there's the gallons per minute. I can manipulate that on here if I wanted to. So there's the hose roll that we're going to use and that we're going to flow water. There's a lot of different things here to worry about. You have your hose lengths, you have your gallons per minute, and you have your friction loss that you want to worry about, as well as the algorithm of actually flowing water. So one thing that I'm going to do is I wanted to talk about some of this stuff first, and next we're going to actually turn the truck on. I'm going to actually get things hooked up as if I was actually at a fire, but we'll slow it down just like I did with my fire gear and show you the simple algorithm for us firefighters that we use in order to actually flow. We're going to turn this on the ignition. We're gonna start her up. Alright, so I have the truck in neutral, N is for neutral, and I have my parking brake on. One thing that I'm gonna do is if I pull up to a fire, I'm gonna have my officer that sits over there, whether it's a captain, lieutenant, chief, I'm gonna have my foot on the brake, and I have this in neutral. And one thing I'm gonna do is go and shift my pump into drive. Now, when I shift the pump into drive, right now it's just like a lawnmower. It's shut off. It's stagnant. It's not on. The truck is on, but the pump isn't on. So what I'm gonna do is there's this little protective piece here so nobody bumps it, and I'm gonna hold this, and I'm gonna flip it. Give it a little second. I'm gonna flip it down towards me another time, and it's saying my pump is engaged. That's good. Green is good. The next thing I'm going to do is I'm going to push D, which means in drive, and this light's going to turn on. I apologize, it's going to be a little loud, but what we're going to do is we're going to hook up our hose line and we're going to flow water. So, as you can see, these threads in this aren't going to connect, so I have to get an adapter. So, we have a 2.5 inch to a 1 3/4 inch, we have to get an adapter. So I'm going to put this on to go bigger to smaller, but I still can't do this, so we have to get another adapter. So we have to do all sorts of different connections sometimes. It's like a puzzle in order for us to get the right connection. So one thing we want to do is right now the water is currently sitting in the tank. We want the water to go from the tank into the pump in order to be pumped out. So as you can call it, tank to pump. So we need to flip that on. So that initiates water to flow out of the tank into the pump to be flowed out. So I remember that we use number 1, 2.5 discharge. Okay, so as you can see outside, the hose line is becoming charged. It's stiff. It's full of water. You can see it's not flat like it was. So now this allows us to flow water. Okay, right? We're flowing water, right? But we don't have any pressure. This is where we go back into talking either RPM mode or pressure mode. I'm going to go in and use pressure mode, but we can increase the PSI to whatever we want. For one of those types of hose, for a hand line, roughly 60 to 100. Otherwise, if it goes too much, it'll literally pick somebody off the ground. So right now on our main discharge pump, we have roughly 20 or 30 PSI. That's the natural pounds per square inch that this truck gives off for pressure. Now, if you watch this, I'm going to increase down here. I'm going to increase the PSI mode. I can hold on to it, and it's going to increase. And I can filter that. I can do it however I want. So right now it's roughly floating at about 80 or 90. So we'll go outside and we'll flow water, and you'll see it'll be a lot more fierce. Oh God, there's people. As you can see, there was a lot more pressure behind this.